Hello everyone. I'm really glad to be here and to attend for the first time CAMLIS. I'm Biagio Montaruli, and today I will present our latest work about adversarial HTML attacks against machine learning phishing web page detectors. So first of all, let me give a big thank you to all the co-authors, so Luca, Demetrio, Maura, Pintor, Luca, Compagna, Davide, Balzarotti, and Battista, Biggio. All right, before digging into the details, let me briefly introduce myself. I'm a PhD candidate at Eurecom, a research center in south of France. And I'm also pursuing my PhD at SAP Security Research. I'm also involved in the Testable European project, which focuses on designing novel security testing methodologies for web applications and machine learning systems. So let's start with the motivations behind this work and then the main takeaways. So this work focuses on phishing. Phishing is one of the most widespread attack vectors that aims to steal sensitive data from users. And as reported by recent report by VID, basically phishing attacks increased by more than 100% quarter over quarter this year. And okay, to counter such type of attacks, machine learning solutions have been defined by both academia and industry. However, machine learning systems are vulnerable to so-called adversarial attacks, and which basically consist in manipulating the input sample in order to evade detection. Now, this work is motivated by two main limitations of the current state of the art. First of all, most of the attacks adopt cheap manipulations. With cheap, I mean simple manipulation that do not fully leverage the domain knowledge about web pages. And second, more importantly, most of the proposed attacks are not optimized against a target model. So to counter such type of limitations, we designed 14 novel adversarial manipulations that are able to evade some state-of-the-art HTML features that are widely used in the literature. And on top of them, we designed a novel black box optimization algorithm that allows you to generate some query efficient adversarial attacks. Indeed, we were able to raise to the ground, just to rephrase the title, or better, to completely evade some state-of-the-art machine learning phishing web page detectors using just 30 queries. All right, so phishing. As said before, the main goal of phishing is to steal credentials from users. And to achieve so, the attacker creates a phishing web page that resembles a legitimate one. Still, phishing attacks is one of the main attack vectors in this landscape in cybersecurity. Indeed, as reported by Kaspersky, the number of phishing attacks basically doubled in 2022, reaching more than 500 million. The same trend is confirmed by Cisco, which reports phishing as the second most adopted attack. So now the question is how to counter, how to fight phishing attacks. Well, first of all, by raising awareness through trainings, so that people are aware how phishing attacks are conducted. And second, by using machine learning solutions to automate detection. So here you can see a basic machine learning systems for detecting phishing web page. We start from a training dataset, including both benign and phishing samples. Then we perform feature extraction to convert each web page into a vector representation. We can also add other pre-processing steps. Then we train a machine learning model so that at test time, given a new web page, it can classify it as phishing or benign. However, as many of you already know, machine learning system can be attacked. And in this landscape, there are several types of attacks. This picture is taken from a really nice paper by Biggio et al. Called White Patterns, in which they try to describe all the possible types of attacks against machine learning systems. In this talk, we will focus on adversarial attacks, which basically consist in manipulating the input sample under some constraints at test time in order to achieve evasion. So basically in order to violate the integrity of the system. Moreover, according to attacker knowledge, such attacks can be classified into white box or black box. And in white box scenario, usually the attacker has full access to the system, he can access to the model, while in black box scenario, basically, usually the attacks are performed by querying the target model. In this work, we will focus on adversarial attacks, assuming a black box scenario. Now, consider again our system. Basically, adversarial attacks can be conducted in two different spaces, a problem space and feature space. So in problem space attacks basically focus on manipulating the code of the input web page. On the other hand, in feature space attacks, basically we manipulate the values of the feature vector. Now, why it is important to focus on problem space adversarial attacks? Well, for three main reasons. First, usually when we want to evaluate the robustness of real-world systems, basically we assume a black box scenario. We don't have access to the model. And usually the model is just one component of the whole system. So classical gradient-based attacks cannot be used. Second, even though we have access to the model, basically if the model is not differentiable, then we cannot again apply gradient-based techniques. And third, more importantly, because of the so-called inverse feature mapping problem. So even if we have access to the model, basically the function that is used to perform feature extraction, so to move from the problem space to the feature space, so to the vector representation, is neither invertible nor differentiable. So if we use gradient-based techniques, we manipulate the feature vector, but then we cannot move back to obtain the corresponding input sample in the problem space. So now the question is how to effectively generate problem space adversarial attacks. Well, in my opinion, the best answer to this question is by using physically realizable manipulations. So manipulations that basically are characterized by two main properties. First, they have to satisfy physical constraints. So in terms of, for instance, format. Also considering our previous example, I have to manipulate the code of the input web page in order to satisfy the rules of HTML grammar. For instance, in case of malware sample, I can manipulate it, but then the resulting manipulated sample must be executable. Second important property is to preserve the original functionality and the original semantic, so the original maliciousness, basically. All right, so how to design adversarial attacks in problem space? Well, we start from a phishing web page, then we need to define a set of functionality and rendering preserving manipulations to ensure that the original functionality and rendering is preserved. Then we define an optimization algorithm. So we use the manipulation and define the algorithm in order to generate a new manipulated web page. And then we have the usual steps. So feature extraction, classification, with the ultimate goal that the manipulated web page is classified as benign, so that we are able to evade the target model. Now, state of the art, we started from a work presented at AXAC called Spacefish. They basically study the effect of problem space attack, in particular based on cheap, simple manipulations. They also considered other evasion space, so website space, so basically it's the problem space, pre-processing space, and the machine learning space. They evaluate 3 different models: CNN, linear models, logistic regression, and random forest. Also considering 3 types of features, so URL, HTML, and a combination of both. In this work also we focus on problem space attacks. In particular, we consider the case of, as for the feature set, we consider HTML features and the combination of both URL and HTML in order to evaluate the robustness of models also trained on the whole set of features. So, as said before, okay, 2 main limitations: the fact that this work focuses on only cheap, simple manipulation that do not fully leverage the domain knowledge about phishing web pages, and attacks are not optimized. As a result, the proposed attacks are, well, not so effective. For instance, in some cases, there is just a little decrease in terms of detection rate, and in others, as you can see, basically the detection rate increases. So basically the attack is becoming kind of useless. Sorry. So now the question is, starting from this work, can we do better? And well, the answer is yes. To do so, in particular, we proposed 14 novel functionality and rendering preserving adversarial manipulations. And on top of them, also we designed a new query efficient black box optimizer that is inspired to mutational based fuzzing. Now, for time constraints, I will just explain one of them, but I mean, if you are interested to the implementation of the other manipulation, we can have a chat and discuss together. So, obfuscate X-link, as name says, basically it's used to obfuscate external link. External links include in the web page, in particular to bypass the feature called HTML SHF, which checks for suspicious HTML forms. Specifically, a form is considered suspicious if it includes an external link, or if it points to a blank web page, or either if basically the action attribute is set to an empty string. As you can see on the left, here we have a web page with a form that includes a malicious link. Basically, we can, using these manipulations, we initialize we substitute the malicious link with a random internal one, and then we include a script. So by using JavaScript, we replace back at runtime the original malicious link. So the functionality basically remains the same, and rendering is not affected. Now, as a reference, I also added this new manipulation that basically allows you to obfuscate diffs elements that are basically hidden. But I would like to move more forward to explain the algorithm and leave more time for the questions. So the input, as for the input of our black box optimizer, we have the initial phishing sample, our F that represents the machine learning phishing web page detectors that we can only query in a black box manner, H that is the function used to manipulate the phishing web pages, the number of mutational routes, and then also basically split the defined manipulation into 2 main sets: single round manipulation and multi-round manipulations. The main difference is that single round manipulations can be just applied one shot, so one time. We do not need to apply them for multiple rounds, while MR manipulations are used to evade other features that requires to be applied for multiple rounds, mutational rounds. So we can split the execution of this algorithm in different phases. So in its phase, we initialize the best adversarial example to the initial one and as well for its score. So single round phase, we try sequentially is each SR manipulation, and if one manipulation reduces the best score found so far, then we update the best adversarial example. So basically, we keep only the manipulations that are effective in reducing the output score. Then we have the multi-round phase. Basically, we execute a loop of different mutational rounds, and in each round, we try sequentially each MR manipulation to generate new candidates. Basically, we use one manipulation for each candidate. Then we take the best among all the candidates, which is the one that with the lowest score. And finally, if such candidates reduce the best score, then it becomes the new best adversarial example found so far. So also in this case, we keep only the manipulations that result effective in reducing the confidence score. And finally, we have the best adversarial phishing example so far, and we return it. Now, these are the results. As you can see on the plot on the left, basically it reports how the detection rate changes with respect to the number of queries. And as you can see, the proposed attacks are able to completely evade all the evaluated machine learning phishing web page detectors. Specifically, we need just 14 queries to evade those trained on only the HTML features. Overall, 30 queries to completely evade those that are trained on the whole set of features. Second important point is that HTML features matter. Indeed, even though the design manipulations are target only the HTML features, they result also very effective also to evade the models trained on the whole set of features. This means that basically the additional URL features do not provide substantial robustness, and so the adversarial robustness mainly relies on the HTML features. Finally, by studying also the effectiveness of the different types of the manipulations, well, the SR manipulations applied at the beginning, so the left side of the plot, considering the vertical line, they allow you to reduce the detection rate up to 50%. And then also applying the MR manipulations, we can significantly let's say increase the attack strength, and also I will say in few queries, basically the detection rate is reduced, arrives near 0. Okay. So wrap up. We proposed 14 novel adversarial manipulations that are that preserve by design the functionality and rendering. So this can be considered as new CVEs for the evaluated machine learning models, and more important for the target features. Then on top of them, we design a very efficient optimized. Here, another important point is that the optimizing, or better, the optimization. So optimizing the choice of the manipulations is the real key of success. This is what is very important when generating adversarial attacks. And this has been also discussed. Here I included some slides presented by Iron at the last edition of RSA, in which basically they tell that the use of algorithms, so based on adversarial machine learning, is really, say, is increased over the years, and especially because last time there was the machine learning security evasion competition focused on evading phishing detectors, and I won the competition using this approach inspired by adversarial machine learning. So we also released the source code on GitHub. Feel free to use it also to foster reproducibility and inspire to a much fairer evaluation of the robustness of models based on for phishing detection. And there is also a preprint available on archive. This work has been also accepted to the AISEC workshop collocated at CCS. So if everyone will be at CCS, hope to let's say discuss more about it. And yeah, that's all. Last but not least, I really would like to thank you, all the organizers, program chair, especially for giving me the possibility to come here with a scholarship. And thank you all for attending this talk.
Thank you. Great talk. Let's take some questions.
How much work went into just identifying the 14 new types of mutations versus like was the focus on trying to drill into that, or more on getting a couple that worked well and then evaluating out the pipeline? Like, do you feel there was like a lot more mutations you could have included in this, or were those most of the good ones you could find?
Well, there is a lot of study about in terms of domain knowledge. So especially in order to understand how to basically bypass the HTML features. So yeah, I mean, it's more, and then also to basically also to define an algorithm. It is, let's say, tailored on such manipulation, especially the fact of clustering the manipulation into different types allow you to speed up the whole process, because usually using just SR manipulation, you can just apply them one time, and this speed ups a lot the let's say the number of queries, so to make also the algorithm much more stealth. Hope
yeah.
I answer.
Okay, sorry, I have a question. So can you introduce like what's the defenders learning, like how we can use the insights from your work to enhance the detectors?
Okay, yeah, nice question. Well, first of all, I think most of the defense relies also on the feature. The features used. So first of all, to design more robust features, there are other techniques that help to increase the robustness. For instance, adversarial training. We tried also in the context of web application firewalls, and we demonstrated that it works quite well. So basically, to integrate into the training adversarial examples generated in this way, still also in the problem space. Yeah, but also, yeah, as said before, I think probably everything starts from designing robust features.
Thank you.
Great. We have time for one more.
Going back to sort of, I guess, what do you call it, adversarial retraining. So if you start putting these adversarial examples back into the training set, how many do you feel you will need until the detector, or is there a number that when the detector will start actually be sort of maybe immune to this attack?
Okay, yeah, nice question. Well, it's, I would say, more an empirical approach, especially when working on problem space attacks. In the work about web application firewalls, basically we used 2000 sample, and basically it worked quite well. I mean, we increased the robustness about more than 25%, if I'm not wrong. So, well, but usually, for instance, in important studies, as you said, to, let's say, start with a lower number of samples and then increase the number to see also how this, which is the effect of increasing the number of other adversarial example included in training set which is the impact on the adversarial robustness. I think there was a study or better a paper presented at Usenix on malware that analyzed this point, like how to change the various settings usually in training and how they impact the robustness.
Great, thank you. Let's do another round of applause.